Hello everyone. Today we are going to analyze this beam using Stiffness Matrix method. In this beam, the support B sinks by 10 mm. The flexural rigidity EI is given as 8000 kN meter square. Before starting the analysis, let us see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is a uniformly distributed load 3 kN per meter and it is acting for the full span. In the span BC, we have a eccentric point load 12.5 kN acting at 4 meter from the point B. The moment of inertia for the span AB is I. For the span BC, it is 2.5 I. Length of the span AB is 8 meter. Length of the span BC is 10 meter. In the point A, there is a fixed support. In the points B and C, there are roller supports. In this beam, we have to find three moments: MAB, MBA, and MBC. Also, we have to find three reactions: RA, RB, and RC. In the point C, there will be no movement because it is a simply supported end. So, MCB will be 0. Now, let us find the fixed end moments. First, in the span AB, let us find them. In the span AB, we have UDL 3 kN per meter acting for the full span. The formula for the fixed end moments are minus WL square upon 12 and positive WL square upon 12. In this problem, the support B is sinking by 10 mm. So we have to also find the fixed end moments due to sinking. The formula for the fixed end moment due to sinking is 6EI delta upon L square. This can be either positive or negative. If the sinking occurs on the right side, this moment will be negative. If the sinking occurs on the left side, this moment will be positive. Let us consider the span AB. In the span AB, the sinking occurs in the point B. So the sinking occurs on the right side. Since the sinking occurs in the right side, the formula for the fixed end moments due to sinking will be negative. In these formulas, let us apply the values. W is 3, L is 8. The delta value is given as millimeter, so we have to convert this into meter. When we divide 10 by 1000, we will get 0.01 meter. Let us apply that value. The value of EI is given in the question as 8000 kN meter square. The formula for the fixed end moment due to sinking will be same for both the M of AB and M of BA. So only one time we have to calculate that and we can apply the same value for M of BA. No need to find it again and waste the time. After the calculations, we are getting M of AB minus 23.5 kN meter and M of BA 8.5 kN meter. Now let us find the fixed end moments in the span BC. In the span BC, there is an eccentric point load 12.5 kN. The formulas for the fixed end moments are minus WAB square upon L square and positive WA square B upon L square. Also, we know that the support B is sinking, so we have to find the fixed end moment due to sinking. We know that this moment either will be positive or negative. Let us consider the span BC. In the span BC, sinking occurs in the left side. If the sinking occurs in the left side, the fixed end moments due to sinking will be positive. Let us apply the values in the formulas. W is 12.5, A is 4, B is 6, L is 10, EI is 8000, delta is 0.01. When we apply the value of EI, we have to be very careful. For the span BC, the moment of inertia is 2.5i, so we have to multiply EI with 2.5. Here we have to be very careful. We know that the fixed end moment due to sinking will be same for both the M of BC and M of CB. So no need to calculate for M of CB, just apply this value here. After the calculations, we are getting M of BC as minus 6 kilonewton meter and M of CB as 24 kilonewton meter. In the stiffness matrix method, when we analyze the beams, we have to check the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope, and in the roller support, there will be slope. In this beam, in the points B and C, there are roller supports. So, the number of supports where slope occurs is 2. In the point B, there is theta B, and in the point C, there is theta C. Now, let us make the fully restrained structure. In the fully restrained structure, in the supports, there will be no slope. We know that only in the fixed support, there will be no slope. So, let us remove the roller supports from the point B and C and replace them with the fixed supports. Now, in this beam, there will be no displacement in the supports. That is why it is called the fully restrained structure. We have made the fully restrained structure. Now, let us make the coordinates diagram. In this analysis, there are two coordinates. We are having the coordinates in the points B and C because in these points only we have the unknown displacement, that is the slope. The coordinates should be made in the clockwise direction. You can see that both of the coordinates are in the clockwise direction. Now let us see the formula to find the slope values. System displacement delta matrix is equal to K matrix inverse into P matrix minus PL matrix. Inside the delta matrix, PL matrix and P matrix, we will have two values because in this analysis there are two coordinates. The size of the stiffness matrix will be 2 cross 2 since there are two coordinates. P matrix is the final forces or moments acting in the coordinate direction. In this analysis, there are two coordinates. In the points B and C, we have the coordinates. In these points, no moment is developed because in the given beam, there is no overhanging. So, inside the P matrix for P1 and P2, we can simply enter 0. So in this formula, we have to only find PL matrix and the stiffness matrix. Now let us find the PL matrix. We know that inside the PL matrix, we will have the moments developed in the coordinates due to the given load. Our first coordinate is in the point B. In the point B, we have calculated two fixed end moments, M of BA and M of BC. We have to add both of them. After adding, we are getting 2.5. Our second coordinate is in the point C. In the point C, we have found a fixed end moment, that is M of CB. Let us apply the value. In this formula, now we are going to make the stiffness matrix. Now let us see how to calculate the stiffness matrix elements. For that, first we have to apply unit displacement in every coordinate. In this analysis, there are two coordinates. In the points B and C, we are having the coordinates. So in these 2 points, we have to apply unit displacement. Then we have to use the formulas. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged, the formula is 2EI upon L. We have to be very careful. We have to apply the unit displacement in the fully restrained structure and not in the given beam. Now in the stiffness matrix, let us find the first row. For that, we have to apply unit displacement in the first coordinate. Our first coordinate is in the point B. In the point B, there is a fixed support. We can assume that when we apply unit displacement in the point B, the fixed support becomes a hinged support because in the fixed support there will be no displacement. Now let us see how to draw this curve. We are applying unit displacement in the point B. The point B is a joint. It is connecting the spans BA and BC. So we have to make two clockwise curves, one curve towards the point A and one curve towards the point C. Both of the curves should be in clockwise direction because we have made the coordinates in the clockwise direction. Then we have to see the direction of the arrows. This arrow indicates upwards, so the curve comes above the span. This arrow indicates downwards, so the curve comes below the span. We have to give some gap between the curves and the fixed supports. You can see that I have given some gap between the fixed supports and the curve because in the fixed supports there will be no slope. K11 should be calculated from the first coordinate. K12 should be calculated from the second coordinate. K11 and K12 should be represented in the clockwise direction since we have made the coordinates in the clockwise direction. Now let us find K11. For that, from the point B, we have to look on both the sides. On the left side, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Length of BA is 8 meter. Let us apply that. Now let us look on the right side. On the right side also there is a fixed support. So we have to apply the same formula for EI upon L. The moment of inertia for BC is 2.5I. So instead of I, we have to apply 2.5I. Length of BC is 10 meter. Let us apply that. For K11, we are having two values. We have to add both of them. After adding, we are getting 1.5 EI. Now let us find K12. For that, from the point C, we have to look on both of the sides. On the right side there is nothing, on the left side there is a hinged support. If the fair end is hinged, the formula for the stiffness is 2EI upon L. The moment of inertia for CB is 2.5I. So instead of I, we have to apply 2.5I. Length of CB is 10 meter. Let us apply that. After calculation for K12, we are getting 0.5 EI. Now let us make the second row in the stiffness matrix. For that, we have to apply the unit displacement in the second coordinate. In the point C, there is a fixed support, but when we apply the unit displacement in the point C, the fixed support becomes a hinged support. Let us see how to draw this curve. In the point C, we are applying unit displacement, so we have to make a clockwise curve towards the point B. Then we have to see the direction of the arrow and draw this curve. We have to give some gap between the fixed support and the curve because in the fixed support there will be no displacement. K21 should be calculated from the first coordinate. K22 should be calculated from the second coordinate. Let us find K21. For that, from the point B, we have to look on both the sides. On the left side, there is no slope curve. If there is no curve, there will be no stiffness. On the right side, there is a hinged support. If the fair end is hinged, the formula for the stiffness is 2EI upon L. The moment of inertia for BC is 2.5I. So instead of I, we have to apply 2.5I. Length of BC is 10. Let us apply that. Finally, for K21, we are getting 0.5 EI. Now, let us find K22. For that, from the point C, we have to look on both the sides. On the right side, there is nothing. On the left side, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. The moment of inertia for CB is 2.5I. So instead of I, we have to apply 2.5I. Length of CB is 10 meter. Let us apply that. Finally, for K22, we are getting EI. In the stiffness matrix, we have calculated both of the rows. Let us apply the values. EI is constant, so let us keep it outside. In this formula, we have found everything. Let us apply them. EI inverse is equal to 1 upon EI. We have to add these two matrices. After adding, we are getting this. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to make inverse in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the inverse. Then we have to multiply these two matrices. After multiplying, we are getting theta B and theta C. Now let us make the slope deflection equations and apply these values and find the final moments. First, let us make the slope deflection equations in the span AB. In these equations, let us apply the fixed end moments. Length of AB is 8 meter. Let us apply that. In the point A, there is a fixed support. In the fixed support, there will be no slope. So, theta A will be 0. After applying the value of theta B, we are getting MAB and MBA. Now, let us make the slope deflection equation in the span BC. No need to make the equation for MCB. We know that it is 0. Let us make the equation for MBC. Here, let us apply the fixed end moment. The moment of inertia for BC is 2.5i. So instead of I, we have to apply 2.5i. Length of BC is 10 meter. Let us apply that. After applying the values of theta B and theta C, we are getting MBC. In this analysis, we have calculated all of the moments. For MAB, we got a negative value. That means it is acting in the anti-clockwise direction. For MBA, we got a positive value. That means it is acting in the clockwise direction. For MBC, we got a negative value. That means it is acting in the anti-clockwise direction. Now let us find the vertical reactions. First, let us take the span AB and find the vertical reactions. In the span AB, there are two movements, MAB, which is acting in the anti-clockwise direction, and MBA, which is acting in the clockwise direction. In this span, first I am going to find RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. The vertical reaction RA is acting in the clockwise direction. So it will be positive and the distance is 8. So 8 RA. The UDL is acting in the anti-clockwise direction, so it will be negative. When the UDL comes, we have to multiply with the distance and distance by 2. Then we have two movements. 21.6 movement is acting in the anti-clockwise direction, so it will be negative. The 12.3 movement is acting in the clockwise direction, so it will be positive. Finally, we are getting RA, which is equal to 13.16 kilonewton. Now let us apply the rule sigma V is 0 and find out RB1. Now let us take the span BC and find the vertical reactions. In the span BC, there is only one movement, MBC, which is acting in the anti-clockwise direction. In this span, first I am going to find RB2. For that, I am going to take moment about C. RB2 is acting in the clockwise direction, so it will be positive and the distance is 10 meter, so 10 RB2. The point load is acting in the anti-clockwise direction, so it will be negative and the distance is 6. So minus 12.5 into 6. Then we have a movement which is acting in the anti-clockwise direction, so it will be negative. After calculations, we are getting RB2, which is equal to 8.73 kilonewton. Then we can apply the rule sigma V is 0 and find out RC. We have found the reaction in the point B 2 times. Let us add RB1 and RB2 so that we will get RB. Now let us make the shear force diagram. Using the reactions and the loads, we can make this diagram. Now we are going to draw the bending moment diagram. Before that, let us make the free movement diagram and the end moment diagram. For making the free movement diagram, we have to assume every span as a separate simply supported beam and calculate the moments. If the UDL is acting for the full span, we have to use this formula. If the eccentric point load is acting in the span, we have to use this formula. Using these values, we can make these diagrams. Let us see how to make the end movement diagram. Using the direction of the movements, we can make the end movement diagram. Now let us combine the free movement diagram and end movement diagram so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.